Can people in the room hear me? Can people on Zoom hear me? Yep. All right. So I need to stay here, I think. Here, it's a bit blurry. I'm here. Trying to do I'm trying to figure out how to fix the back of this video. The video's not working. This is weird. Is anyone in the back room and can like adjust the projector a bit? It looks a bit blurry.
You wanted to see if it's your laptop or mine?
It's definitely not the laptop. This looks like a
Well, it looks like a 640 by 480, but maybe the audio. Oh, yeah, it looks like a focus thing. Sure does.
You're right. Yeah. I can't change that in a sense. Oh, yeah. Sorry, I wasn't here. All right. Good afternoon. How's everyone doing? Excited for the long weekend? Yeah? All right, let's see what's coming up over the next few days. Lab 4 is due today. Just how are people doing on that? Doing well? All right. Other than that, we have Project 1B that's going to be due this Wednesday. And then our midterm is Thursday. We will have one review session on Wednesday when we come back. So does anyone want to like shout out any topics that you want covered? Yeah. What's up? Sorry, I can't hear the question that's being asked. Can everyone? Uh, oh yeah, you could bring. Oh, throw the cube. Oh, huh. Does the cube actually work?
I'll work on it. Go ahead.
All right. Yeah, you'll be getting an email saying which room you'll be assigned to. Yeah. All right. So let's just quickly. I do.
Right now we're on
I'm on. I have using it.
All
Yeah,
right.
I can switch to HDMI.
Yeah.
All right. Where's the?
That's my
Where's the other HDMI cable? This is the HDMI cable.
Here's this. Here.
There it is.
See that one. All right, see if it will. Might have been
Let's
I
try.
agree that it was Oh, no.
All right. Anyway, what do y'all want covered for tomorrow or for Wednesday's review lecture? We had some from last time. I want to ask this class here. Anything? Yeah. Class inheritance and what? And interfaces. I heard it right here. Comparators versus comparables. Okay. Anything else? Josh is getting a runaround. Golden rule of equals. Yeah. Linked lists. All right. Any other topics? Last call. We're going to decide. Huh? Projects are considered within scope. Yeah. Sentinels. Generics. Static classes and methods. All right. Compiler versus runtime errors. Yeah.
Divas. Oh my God.
Divas. Wait, what?
D-lists.
Oh, D-lists. I heard divas. All right. Sounds good. All right. Let's start today's lecture. So today we're going to be introducing a new topic. This is not going to be considered within scope for the midterm. It's kind of going to be an intro to the first topic we cover after the midterm. And this will be kind of the most math-focused sequence that we have. So welcome to Math 61B. Now, this isn't quite a math class. We're not going to go as rigorous as a full math class, but it is going to get fairly like mathy. So whenever we're an engineer, right, our goal is to get something working, but it's not just to get something working, but it's to get something working well. There's a saying that an engineer will do for a dime what any fool will do for a dollar. And that kind of means that as an engineer, our goal isn't just to make something, but to make something using the fewest resources that we can. Now, for a computer scientist, there's two types of efficiency we think about. One is how much it takes to actually program the thing. So how long does it take to actually write your code? Can you write it quickly? Can you maintain it a long time? All of those are things that we've covered so far, and we are going to come back to this during our software engineering lectures. But from now on, we're also going to be considering how do we efficiently write code, or how does the code that we write run efficiently? So we want to write programs that don't use too much memory, that don't use too much time. We don't want a login page that takes 3 days to log yourself in. That's not useful for anyone. So we're going to try and figure out ways to reduce the runtime of our programs. And for today, we'll be looking at how do we measure that efficiency. Let's have this as kind of our toy exercise. We're going to be trying to solve this problem. And our problem is, if we have this array and we know that it's already sorted, how can we check to see if there are any duplicates? So first off, is this true or not? Does this array contain duplicates? Yes. What is the duplicate? 4. How would you write an algorithm to solve this problem? Let's, yeah. Yeah, because you know this is already sorted, let's come back to this actually in a bit. Is there a sillier solution that the first thing you can think about?
Create a complement and then we traverse over each of the element in the order. Like,
I think you have a similar idea. The silly approach is check everything, right? I'm going to check. Is -3 equal to -1? No. Is -3 equal to 2? No. Is -3 equal to 4? No. Is -3 equal to 4? No. And I keep going in every single one of these pairs until I find a pair. And if there is any pair, then I'm going to call it true. Otherwise, it's false. The better way, as you mentioned, since we know this is sorted, we can just look at adjacent items. If there is any pair that is the same, then they're going to be right next to each other in the array. So we only need to check -3 to -1, -1 to 2, 2 to 4, 4 to 4, 4 to 8, 8 to 10, and 10 to 12. So what we're going to do is we're trying to formalize why we think that this second algorithm is better. Now, our general approach for this class is going to be kind of 2 steps. First, we're going to say what we mean by better. We're defining some metric of how we consider efficiency. So this might be, for example, how much time it takes to run a program, how much memory the program uses. Not necessarily for this class, but you might have cases where you're looking at the average error for some randomized functions or functions that don't quite get the right result, but get close enough to be right. Once we have that, we'll be able to classify our efficiency according to some mathematical framework. We're going to classify our efficiency according to some of its properties. And we're going to try to get a classification that's simple, rigorous, and model the program's efficiency good enough that it works for our purposes. So I will point out throughout this sequence, we are going to be using 2 different definitions of the word function. One of them is the concept of like a program's method, right? A program has a function that is a sequence of instructions that you run. In math, a function is more kind of a map. You take in an input, you receive an output, and for every single input, there's a distinct output. So kind of more like a dictionary in a Python sense than an actual function in a Python sense. So keep that in mind. I'm going to try to use the word function exclusively for the mathematical sense and program exclusively for the computer science sense, but I might make mistakes here and there. So let's try and discuss this. First off, what do we mean by dupe 2 is better? What is our like exact definition of dupe 2 being better? Yeah.
One loop versus 2 loops, so I guess you could say
you are jumping really far ahead in the class. Yeah. Yeah. Dupe 2, I would say, is better because it does fewer steps to accomplish the same task. So another way to say this is dupe 1 does more work and takes longer to run just to get the same result. So intuitively, we think that dupe 2 is better, and we think it's better specifically because it takes a shorter time to run. It takes less steps, so it's going to run faster. So for the rest of today's lecture, our metric is just going to be runtime. We're going to be comparing the runtimes of these 2 functions to determine which one is better. Or rather, we know which one's better. We're going to classify them and actually quantify how that much better dupe 2 is. So how do we do that? What's our first idea on how we can quantify how fast dupe 1 runs versus how fast dupe 2 runs?
Like every time you run some code, like you add a counter and then you just calculate the counter.
All right, we could have a counter of some kind. Is there like a simpler, just first thing that comes to mind? How do we determine which one runs longer? Time? Yeah? Yeah, let's time it. So what I'm going to do is I'm going to get out this code. I have dupe 1 and dupe 2 written right here. And I have this code that is just designed specifically to run the function. It's going to run successfully larger versions of this code until it gets too slow to run. So if I run this right now, is this large enough for you to see? No.
I think you could just.
How's this? It's bigger a bit. Anyway, so we can see that dupe 1 It takes 0.002 seconds to complete a size 1000 array. That's really good. But as it grows bigger, 2000 takes 0 seconds, 4000, 5 milliseconds. By the time you've hit 512,000 items, you're at 20 seconds worth. How about for Dupe 2? Do you think this is going to be better or worse? Better? All right, let's run this. All right, we've already gotten to 524 million, and yeah, it gets so big that the problem isn't the fact that it's running slow, but it's Java just ran out of memory to store the array. So for all intents and purposes, Dupe 2 seems like it's going to be fast enough for any size that we want. Dupe 1 seems like it struggles somewhere around the 500,000 point. All right. So we could just evaluate this, just run a stopwatch, check the time. And if we do, we might get some function like this. This is, I think, when Josh tried to run this a few years back. I think my computer is slightly beefier because it's running faster than this. How do you think? Do you think this shows us that Dupe 2 is better? Any issues with this, maybe? Yeah? Yeah, the runtime changes depending on the computer, right? As we mentioned, right? This was done when Josh had his computer. His computer was slower than mine. Mine was able to go really far, much farther than these. And in fact, it's not just different computers. I have the same code in Python here. And if I tried to run it in Python, is it this one? Yeah. This one, it slows down by the time I hit 8,000. Like, this is way, way slower. Did my code just suddenly get 100 times worse just because I switched to Python? It's Python's problem? No, it's our problem. We're the ones who wrote the code. Yeah. It feels like there's something to do with the language that will affect things, and we don't want that to affect our ultimate like code. The algorithm itself isn't being changed. It's just the language, and that shouldn't affect our classification at all. We could try running this on Dupe 2. And one thing we might notice, let's just run it on Dupe 2. We might try first step to look for commonalities. And, after a while, eventually you might come to this conclusion of just trying to see what the differences is between each round. So every time you double the size of the input, just kind of get a sense of how much the runtime increases. And if you do that, you will notice that for Dupe 2, or Dupe 1, sorry, this number stays around 4 for the Python version. And also, if you run on Dupe 1 on Java, it also ends up converging to around 4. This feels like something that will be consistent across a lot of things. In fact, if I tried to run this on Josh's computer, or I tried to run this in another programming language, regardless of how I do this, and I try to do this, I'll generally get around 4 for this one, and around 2 for Dupe 2. This seems like there's something mathematically going on that seems more fundamental to the actual program itself than all these like random things. Keep that in mind. We'll come back to this in a bit. But as it turns out, like the main issue with this, at the very least, it's easy to measure. The meaning is obvious, but unfortunately, it does depend on the particular machine, depend on the particular program language. You're going to get different times for those. So we don't like that too much. Another big issue is that in order to test something like this, we need to actually run the code for that long. I don't necessarily want to run the code for hours on end just to show that it's too slow to run. So it might be useful for like initial like experiments, but it's not a mathematically rigorous approach. One thing we do note, though, is that if you double the size of the input, Dupe 1 always consistently takes 4 times longer, while Dupe 2 consistently has a factor of 2 size increase. If we had run the Dupe 2, it would be 2 times. I'm just skipping that now for time purposes. And this is actually true regardless of what language you use and what machine you use. So if just counting time doesn't work, how do we actually fix that? Well, we want something that's not associated with the runtime itself. We want something that's more associated with the code. And one thing that might work, as was mentioned up here, is let's just have a counter that counts how many times we do stuff. So here's how we might do this. Let's just pick some random array of size, let's say 10,000. And we're going to run this and count how many times each operation happens. So if we have an array of size 10,000, I equals 0 happens exactly once. It only occurs once because this int I equals 0 line only exists in that spot. Unfortunately, these computations are going to be tricky. Depending on the particular array of size n, we might get some number between 1 and 10,000 for the number of times j equals I plus 1 happens. We'll get between 2 and 50 million operations of less than, between 0 and 50 million operations of plus equals, and so on and so forth. Overall, we can expect that for an array of size 10,000, we're going to get about 100 million operations, up to plus or minus a factor of 2 or 3. That's quite a few operations. How do people feel about this? Yeah? Yeah, as your program gets bigger and more complex, it's going to be hard to track all these operations. That's true. Any other potential issues with this approach? Yeah. Well, yeah, it is inefficient to have a lot of these operations, but that's more of an issue with this code. I'm talking more about like, are there any issues with like this approach of classifying this function according to checking an array of size 10,000? Yeah. Yeah, like why did I specifically pick these operations as the ones to care for? What if I said that instead of all these operations, I had a single operation that evaluated the entire AI equals AJ? I'm going to have smaller numbers. Does that mean my code got better? Not really. Uh, I would say it's also kind of hard to compute this. Like we kind of skipped over a lot of the computation process. Also, why did we pick 10,000? 10,000 seems like a random number. I'm not entirely sure why 10,000 is necessary. What if 100,000 Duke 2 gets worse? And also, like, depending on the particular array that you pick of size 10,000, you're going to get a different number of operations. On the other hand, this is machine independent. We are able to ignore actually trying to run the code. And so we don't get into variation depending on which machine we run it on. How do we fix some of these issues? Well, let's try this. I'm going to say, instead of counting these in terms of 10,000, I'm going to just turn these into functions. Interpret this in terms of n. So if I do this, I'll eventually get to these numbers. It's a bit tricky to get these numbers. We'll talk about this a bit later. How do we feel about this? Having these symbolic counts that say between there's exactly 1 to n operations of j equals I plus 1, exactly n squared minus n array accesses, or up to. How do we feel about this? Good? Bad? Any issues? Well, I'd personally say that this is good. It does tell you how the algorithm scales, which is really nice. We're not just looking at how much time it takes for one particular input. We're looking at how it grows with time or with n. But it's still really hard to compute. And it also like has a lot of this complexity. As you mentioned, if we combine some of these operations, we are going to get a different number. And I also argue that this isn't quite a function quite yet. Because if we take an input of size n, let's say 10,000, there's going to be different possible number of operations that you have depending on that particular input. It's not a one-to-one function. There's not one specific value that's associated with f of n. There's multiple values. And that's not really nice to work from a mathematical perspective. So we're going to fix some of these issues. First, let's try and fix the issue that this isn't actually a function. What I'm going to do, and this is kind of tricky, is I'm going to just pick one particular input to represent each input size. So the most common cases is I'm going to say the worst case input is always the one we care about. And sometimes I'll say the best case input is the one we're always caring about. So for this program, what input takes the most time to run? Yeah? Yeah. If we don't have any duplicates at all, we never hit this return true statement in the middle. So therefore, we have to iterate through every single item twice. So it's going to take the most time. So our worst case input for this function is going to be the one which has no duplicate items. What about the best case? What input would give us a best case time? It runs in the fewest operations possible. Yeah. Yeah, if the first two entries are the same, what happens? Well, we check between 0 and 1. 0 and 1 are the same. We return true immediately. We don't go through any more iterations. So here are some examples of some of the worst case and best case inputs. A worst case input is something that takes in all distinct items. Best case input, you only really need the first two items to be the same. I just picked an array that's all fours. So what we'll do is we'll look at each of these separately. And I'm going to say for most of today, we're going to be discussing the worst case input, mostly because that's the one that looks most interesting. The best case input, you kind of just do 5 or 6 operations and you're done. So if we do this and we do all the math, then we'll end up showing that if you have an array of no duplicates, then it takes 1 I equals 0, n j equals I plus 1s, n squared plus 3n plus 2 over 2 less thans, and so on and so forth. So what do we think about this? It's now a function, but it still has some of those issues. It's still tedious to compute, and this result is a function. It takes in as input a number n, and it outputs some tuple of values, but it's a table of values. It's still really hard to compare things. At the very least, though, it is something that we can work with. So let's just try that out. For now, let's try this out. For dup2, can we figure out what the best and worst case operation counts are? And don't worry about being off by a bit. Feel free to talk with your neighbor. Let's come back in 2 minutes. Yes.
Why? Yeah, maybe. They didn't start to write a visual. Yeah. Right. And that's thinking like, oh, that's that. Yeah, where'd it come from? Yeah. But I mean, I don't know.
Well, I'm explaining where it goes.
Right. Eventually, right. But like, yeah, I was trying to think of how I would make that for interesting thing. Yeah. There's that word that happens.
Yeah, I personally just say, like, imagine that you just try a bunch of things and right? Yeah. We make that operation, but we'll come to explain why that actually is.
I think what if we have for me is a runtime table, and then we'll arrow. This row is 4 times bigger. Then you know where this one is.
Yeah.
I mean,
Actually,
that guy goes. Some of these guys, you know, this
Yeah.
they totally
I think also in the back it's front.
right. Could be right.
Yeah.
Oh yeah, I'm curious.
It's a bit better now, actually. All right. All right. Test. All right, let's bring everyone back. What did everyone get? How many less thans occur in the best case? 1. Worst case? N or N minus 1, somewhere around there. I don't particularly care about off by ones, as long as you're close enough. How about increments? How many times does the increment happen in the best case? 1? 0? Somewhere around there, 1 or 0. Worst case? N minus 1? Okay. Equals? 1 in the best case? How many times in the worst case? N minus 1 in the worst case? How about array accesses? 2 in the best case? 2n minus 2 in the worst case. Those seem about right. Yeah. So overall, if we count all this, we end up with this many operations. Don't worry if you're off by 1 or 2. It's not too important to get the exact values, as we'll see later. We also kind of ignored a few operations here, like this -1 and this +1. We'll show why we don't actually need to worry about all of those operations exactly in a bit. So this works. We do get some function. We're going to try now to classify this function properly. Get it down to some easy to explain metric. Some way that we can say to someone else, oh, this function is this type of thing, without saying, oh, this function has n squared array accesses plus n addition operations plus. That's too complicated. So first off, which algorithm is better? Just from looking at this table. Dupe 2. All right. Why is Dupe 2 better? Huh? Smaller order of growth. That is a good point. Yeah. First off, all these numbers are smaller on the left side or on the right side than the left side. So it's clearly better on the right side. But you make a good point that it's a smaller order of growth. That's actually more important here. The algorithm scales better in the worst case. And when we say it has a smaller order of growth, you're effectively saying that the parabola, the n squared parabola, it's going to grow faster than any line n does. Let's try and formalize that. In most of these cases, when we're working with a program, we're looking at the order of growth more than anything. We only really care about this runtime when our data gets really, really big. So we look at how the data behaves as we approach infinity. That's kind of like the asymptotic behavior. So we might be looking at billions of particles or billions of bytes of data. Those are the ones that take the most time. So those are the ones that we focus on the most. The algorithms which scale well are generally going to have better asymptotic runtime behavior than the ones that scale poorly. And since scaling matters so much, we'll be focusing more on those. Here's kind of a quick example. Suppose that we have some algorithm ZERP. I'm not sure what ZERP does, but it's going to ZERPify some collection of items. But ZERP 1 takes 2 n squared operations, whereas ZERP 2 takes 500 n operations. Which one's better? ZERP 2? Okay, but I try running this algorithm, and I look at this graph I get, and ZERP 1 is always faster than ZERP 2, up until 100 at least. Why is ZERP 1 better? Why is ZERP 1 worse? Sorry. ZERP 1 was faster, but why is it worse?
It's the number of n gets larger, it's gonna intersect.
You're saying that as we get bigger, maybe things are going to change? Well, let's try it out. Let's say I test a larger thing, and yeah, I'm starting to see that ZERP 1 is starting to grow larger. But it's still 50-50 in my perspective, right? Half the time it's better, half the time it's worse. But as I keep growing, yeah, ZERP 1 is clearly growing way, way faster than ZERP 2 is. So eventually ZERP 1 is going to become slower. And because we only care about these really big sizes, we're going to end up needing to look more about the order of growth. Why do we only care about these big sizes? Well, computers are really, really fast. If you look at how much computers can do, right? A human, I can do maybe one math operation per second at best. My Python code, it's really slow, but it still does a million things per second. That's just my approximation about how much Python does. Meanwhile, if I just run it on an actually fast programming language, I'm doing a billion things per second. And if I do some special tricks to get it to work on my GPU, my graphics chip instead, then I have up to 1 trillion operations per second, just off like standard day-to-day computers. So let's look at kind of how these behave. If I look at n squared versus n squared plus n versus 2n squared, all of those seem to be fairly similar as we grow larger. Like the difference between n squared and n squared plus n is 1 for pretty much the entirety of these. A difference of like 1 is not relevant at all when you're dealing with arrays of size 7 million. Meanwhile, if I look at the 500n, 500n, it's so slow that I can't even do size 1 array as a human. But I can do a size 120,000 array in Python. That's even bigger than the n squared one. And by the time I hit 1 trillion operations per second, I have 5 digits more on that one. That's like 100,000 times better than the n squared version. Meanwhile, the n cubed one, at the human level, it's really fast because I have this small coefficient at the start. I can get up to a size 39 array done. That's way better than even n squared. But as we keep getting faster and faster computers, we end up having this n cubed factor take up more of our time, and we end up causing our maximum n to become much slower. By the time you hit 1 trillion operations per second, you're only doing 390,000 items in your array, which is about what? 1/20th the size of the n squared version. Effectively, as we get larger and larger computations, the size of the array that we can compute in a feasible time depends much more heavily on this n squared than it does on the n or the n, or than it does on the constant factors in the exact times. In fact, if we just look at these, we often like to say like this function is an n, this function is an n log n. We have these tables that kind of say how fast things grow. And we'll formalize this soon. But in effect, if we can get something down from an n squared to an n, that's the difference between 3 hours of work and 1 second of work. A difference from n cubed to n squared, that's the difference between 32 years of work and 3 hours of work. I do not want to wait 32 years to get the result of some program. So generally speaking, I'm not going to like an n cubed operation if I have to deal with 100,000 items. Yeah. So this characterization is really nice. From 61A terminology, we might have used the word quadratic and linear. Is it mathematically rigorous? Not really. I kind of just said this looks like a parabola, this looks like a line. I want to be able to say this is actually mathematically true. But on the other hand, it is simple, and it does demonstrate the superiority of dupe 2 over dupe 1. So our goal is to say how dupe 1 is quadratic specifically, and kind of prove it mathematically that it means a quadratic. Any questions coming up to here? All right.
Wait, you were just saying that polynomials are like dominated by like the power?
Are polynomials always dominated by their highest power? Good question. We are going to figure that out. We're going to have to prove that, but it seems like a reasonable thing to state. So our goal is to characterize the runtime. So first off, let's try to convert it into a proper runtime function. I just want to ask, if I had this table, what do you think the overall runtime is going to be? How many people say this runtime is going to be n? It's going to be a linear runtime function if we have a function of this time. We don't know its exact time because we don't know how much time array accesses take, for example. But do we think it's going to grow linearly? How about quadratically? Cubically? How about sextically? Seems like a lot of people said cubic. Why did you say cubic? It's the highest term? Yeah, that's a good argument. Here's kind of a more formalized argument. Let's say that the array accesses take alpha nanoseconds, where alpha is some variable. The greater than takes beta nanoseconds, where beta is some variable as well. and the print statements take gamma nanoseconds. If we add all the time that it takes to run this, then it takes this much time. And as long as n is large enough, that 2 beta n cubed term is going to be the one that dominates everything else. All the others are negligible because they grow slower than the n cubed does. And that's true regardless of the values of alpha, beta, and gamma. If you want to get like actual values that might exist, alpha is probably somewhere around 10 to 100 for really fast array accesses. Greater than is probably going to be around 1 or 0.1 even for a really fast computer. Print statements are going to be around 1,000,000. Print statements are really, really slow. But regardless of that, eventually the n cubed term is going to grow larger, so we don't even need to look at what these alpha, beta, and gamma are. Now, let me ask this question. What do you think the growth of dup1 should be? What do we want this to be? We want an n squared of some kind? Yeah. We add up the n squared coefficients to get 2.5 n squared. That's interesting. Do we know necessarily that these are all, well, actually I'll get to that, but we do want something n squared-ish. That's a good point. So ideally we do want to classify this as n squared. So let's try and do that. Our goal is going to be to try to mathematically show that this is an n squared. And we're going to be looking at some simplifications to get it down to n squared and making sure that all of our simplifications don't affect what we really care about, the most important modeling aspects of this. So first off, I'm going to do what I did earlier. I'm going to assign variables for each of these runtime costs. And I'm going to say that the worst case runtime is equal to this complicated function. Alpha plus beta times n plus gamma times, there's too many of these. Eventually, if you evaluate this, you end up at this equation here. Some sequence of operations times n squared plus something times n plus some constant amount. Fair enough. We don't have a table anymore. We now have some equation. It's got a lot of variables, but we're going to get rid of those soon. Our next simplification is I'm just going to ignore all these lower order terms. Why do I do that? Well, they're not going to grow fast enough to affect things. We do need to prove this, and we are going to do that next week. But for now, we can say that it's reasonable enough to say that the n squared is eventually going to grow fast enough that all of these are too small. They're not going to affect things. And also we say that the lower order terms aren't actually going to be affecting things. We're going to assume those for now. We'll prove those in a later class. Our third step, you mentioned that it is 2.5 n squared because you kind of add those up. But that really depends on what the value of gamma, delta, epsilon, and zeta are, right? Depending, gamma might be 100 and delta might be 1. And in that case, it doesn't make sense to call it 2.5. What we're going to do is we're just going to combine all those into a single constant. And we don't actually know much about that constant because it could be pretty much anything depending on what the function is. So I'm going to say I don't actually care about what that constant is. It could be anything, and it doesn't actually convey information about the code itself. Depending on the machine, you've got different values of C. So I'm just going to say that it is n squared. I still need to note that the constant exists. So I'm going to group together all functions that are of the form C n squared, and I'm going to call this group the theta n squared class. So when I say the worst case runtime is a function in the theta class theta n squared, I'm saying that the theta n squared class is a group of functions that contains our worst case runtime. I don't know where in the theta n squared it is, but it is somewhere within that classification. Using all these simplifications, we were able to get from this really complicated table all the way down to this simple statement. The runtime is theta n squared. And theta n squared is something I can say to someone. It's very fast. Does it convey all the information we need about it? Well, let's see that soon. For now, let's ask this. What is dup2's worst case runtime? What would you say if we ran this exact same operation? Let's take a minute or so to do that. All right. Let's bring everyone back. Uh, what did people say? Uh, Someone from maybe the back half of the class, because I think the front half keeps. Yeah. You think it's contained in theta of n? Why do you say that? Yeah, that seems reasonable. All of these are n or lower, and we are ignoring all the coefficients. So we're going to say it's theta of n. I think that's reasonable to say. So this is theta of n, while this one is theta n squared. Which one's better, theta n squared or theta n? Theta n. So it does seem like this is a simple, clear, and mathematically rigorous way to say things. One thing I will note, if you look at this theta n squared, right? If you take n and scale to n squared, and you double the size of n, then n squared quadruples to 4n squared. That's where we get that 4 times from before, right? We saw that when we doubled the size of the input of dup1, we ended up with 4 times more runtime. And that's true for anything in n squared. So even though we did all these simplifications, we still are ending up capturing the essence of the program's runtime itself. That fact that every single time we doubled the input, we got quadruple the runtime, that is captured by our model. So that gives some sense that the model is probably capturing what we want to capture. So our overall process, we have to construct a table of all these counts, convert it into a runtime function, and then classify that. That's a lot of work. I don't want to do that. But if we use our simplifications from the outset, we're going to be able to avoid building this table entirely. Let's take a look at how we might do that. And this time, we're going to show all of our work. So first off, we're going to treat anything that takes constant time as a single operation. Why? Any coefficients that are going to be ignored by our theta class anyway. So 5 operations, 1 operation, they're the same thing pretty much. Then we'll figure out the order of growth, making an exact count, discarding some pieces. We might use some intuition to try and figure things out, but that's only really possible with a lot of practice. So we'll have to go through them hard way first. So let's try and do our analysis of dup1 using this. So here's our code. And because I'm dealing with the worst case runtime, I'm going to say that that return true never returns true. It's always going to fail that. We'll never go into that code. So what I'm going to do is I'm going to first add a simplification that this center part is just 1 unit of work. I don't know how much time that actually takes. I just know that it's a constant time. It's not affected by how large n is. It is 1 unit of work. And then what I'm going to do is I'm going to make this diagram. I'm going to look at every single unit of work, and I'll kind of map it on this ij plot. And I'll see that for I equals 0, there's like 1 unit work for j equals 1 through 5. For I equals 1, there's 1 unit work for j equals 2 through 5, and so on and so forth. Our total number of units of work is this function here, 1 plus 2 plus 3 plus all the way up to n minus 1. How do we simplify that? Well, one approach, if you're one approach, this used to be a famous story about how Gauss, when he was 10 years old, came to this idea to try and flip this equation. If you do that and then add it piecewise, then you get a bunch of n's added together. How many of these n's are there? N minus 1 of them, because we go from 1 up to n minus 1. So we have n times n minus 1 is equal to 2 times this, and then if you divide, you get n times n minus 1 over 2. There's the story that Gauss figured this out when he's 10. Gauss was also extremely brilliant and crazy. This is kind of a neat trick to use. It's also tricky to figure out on your own, though. Huh? Is this geometric? I wouldn't call it a geometric series because the meaning of geometric series is actually an entirely different thing. We would call this more an arithmetic series. Yeah. Isn't it n minus 1 times n minus 2? I don't think so. I believe that there's n minus 1 of these items, right? You go from 1, 2, 3 up to n minus 1. And then you have add up each one individually to get n.
Yeah.
You might be thinking it's n minus 1 times n minus 1 plus 1, which would be n. Yeah. Now, I might want a simpler version. I might say, what does this thing look like to you? This blue area. What is this blue thing? It looks like a triangle, right? And the total number of ones, it's about the same as the area of this triangle. So what's the area of a triangle? Yeah, base times height divided by 2. If you do that, that's n for each, the base and the height, just about n. It's not exactly n, divided by 2. We ignore the coefficient. Either way, we end up getting a theta n squared bound. All right. Any questions on this? We'll try and show this in more detail next Friday. All right. Now I want to finish off today's lecture by formalizing everything that we've done. So what we basically did was we took our equation and we just kind of took the largest term and applied simplifications to the point that we could say the order of growth was just that largest term. We did say that it's a theta class, but we didn't really define what a theta class is. I'll finish off today by saying what a theta class is. The math might seem a bit hard to work with, but the idea is effectively the same. We're just formalizing these simplifications into an equation itself. Our main simplifications are we don't care about small cases, and we also don't care about being off by a small factor too much. All right, I got like one more slide left. Please stay for a bit. Here is our official definition. This is very complicated, but we can go through this one step at a time. First off, we want to say that we don't care about being off by a constant factor. So what this is saying is that R of n is defined to be within the theta class f of n if f of n times some constant is always less than R of n, and f of n times a constant is always greater than R of n. So that means R of n is somewhere between, let's say, 5 times f of n and 7 times f of n. That covers the fact that it's not, we don't care about any constant factors. And we also don't say it needs to be greater for all values of n. We only say that this bound needs to hold for sufficiently large values of n. So there's some n naught value that everything after that is going to be fulfilling this bound. We're going to have to do more about this next week. We'll talk more about the math there. But for now, let's think about this, or we'll leave off with this definition. We'll use this in more detail Friday.